it never really made sense to me because of instruments.
Mm-hmm.
Like if you have like a guitar,
Mm-hmm.
how then it would resonate with multiple frequencies. So,
It's a different frequency.
Yeah, there's a force vibration. I understand where the confusion's coming in.
okay.
Let's sort that out. First, the idea of natural frequency. That's an important thing. Everything, if it is disturbed, will vibrate at a natural frequency. Okay. What I tend to think of is like a swing with a kid on it. So if we picture we have a kid hanging, a swing set here and a kid hanging on it, and you push, that swing set is going to vibrate at some natural frequency, okay? And if I come up and try and force it to vibrate at some other frequency, it's not going to work real well, and the kid will still move. But if, for example, if the kid's hanging here and I come up and push thump, 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 they're not going to swing very high, even though I put a lot of energy into it. Because I was operating at this frequency, thump, 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 but the swing was operating at swing, swing, that frequency. And those two are different. So when I gave a push, it started the swing going, but when I pushed it the second time, it was still heading that way. So those two pushes might have added together and gave it a little bit bigger boost. But by the time I gave it the third push, it was heading back this way, and I just canceled out a bunch of my force. So my pushes sometimes add to the swing and sometimes cancel out, and I end up with no great motion. Okay? Now, on the other hand, if I push exactly in time with the natural frequency, so if the natural frequency of the swing is swing, swing, and I come up and push exactly in that, I push, I wait for them to come back, I push again, wait for them to come back. My push is exactly the same frequency as the natural frequency of the swing. Now, all of the interference is constructive. It always makes it increase the amplitude, and so it gets bigger and bigger and bigger and bigger. With sound waves, we typically hear that as its sound getting louder and louder and louder. Do you remember the aluminum rods that we made sing real loud and obnoxious? Okay. That's a really good example of resonance with a sound wave. Now there's a similar effect that can happen, like if I take a tuning fork and hold it on a big flat surface.
Which is sounding board.
Right. Can you hear it get louder? Okay. That is not resonance. Now the effect is similar to resonance in that it got louder, but the cause was because I was causing a great big surface area to vibrate.
Okay.
So in like an acoustic guitar, you have some resonance going on, but the main thing is you've got a big surface area that you're forcing to vibrate, and it vibrates. Since you're forcing a big surface to vibrate, it moves a lot more air molecules, which increases the sound.
So the soundboard isn't resonating?
Yeah, that's not necessarily resonance.
Oh, okay.
That's forced vibration of a large surface area. Now, say a lot of times you'll hear people use the term resonance there because, again, the effect is very, very similar, but it's not really resonance. Okay? Now, suppose that that molecule inside the glass happens to have a natural frequency that matches the frequency of our photon that comes in. Okay, because the photon is going to have a frequency. So suppose you've got a molecule that its natural frequency happens to match the frequency of this photon. Well, when this photon comes in and hits, that photon is going to be hitting this molecule or atom at its natural frequency, so the excitation gets larger and larger. So that thing just kind of tends to absorb more and more energy. The vibration of the whole molecule gets bigger and bigger. It doesn't just absorb and drop back and re-emit. It absorbs and absorbs and absorbs, and the whole thing gets moving faster and faster. So the entire molecule, the entire material then, begins to absorb more and more energy. And what's going to happen to the temperature of it? It's going to go up because that energy is being absorbed. Whereas our transparent material, what was happening to the temperature of it?
Passing it through.
Yeah, not really changing much because it was just, absorb, pass on, absorb, pass on. But now this is causing that energy to actually be turned into kinetic energy, which is probably going to be producing some infrared light, which is frequency of light at a lower level than what we have. So this stuff is now going to be absorbing the energy and going on. So if the material is made of something that has molecules in it that resonate at the frequency, say, of visible light, then for visible light, we would say that stuff is opaque. Okay? If the material is made of atoms and molecules that none of them resonate in the range of visible light, then we say, well, that's transparent. So glass, which is made of silicon dioxide, we look at glass and we say, well, that stuff's transparent. Light passes right on through it. If we could see ultraviolet light, however, if you looked at that window and all you could see was ultraviolet light, you'd look at that window and you'd just see a black spot there. It would appear to be a solid wall. Because ultraviolet light doesn't pass through glass. It's opaque to ultraviolet light. So ultraviolet light is the stuff that causes sunburns. So why is it that if you drive in your car and it's sunny and the sun is coming through the window, you don't get a sunburn inside your car, even if the sun comes through the window and shines on you? Because the visible light, all the stuff you see comes on through. The infrared, the heat, the warmth stuff comes on through, but the ultraviolet light that causes the sunburns doesn't pass through. So it's opaque to ultraviolet light. The wall right here, that concrete block wall, when I look at that, I say, well, in terms of visible light, that's an opaque material. Visible light does not pass through that wall. But do any electromagnetic waves pass through that wall?
Gamma rays, X-rays.
Gamma rays would. If I had a radio in my hand, radio is probably going to come right on through. So some wavelengths will pass right on through. So just because a material is opaque to one wavelength of light doesn't mean it's going to be opaque to other wavelengths of light.
You're saying that glass stuff's UV rays?
Yes.
Does all glass stuff UV rays, or is it just the stuff that they market?
Silicon dioxide glass absorbs UV. Now UV is actually kind of a spectrum. You get into it, they'll talk about UVA and UVB, and the difference is one of them is a little bit higher frequency than the other. But glass absorbs UV, and a small percentage of some of them will come through. But basically, if it's made of silicon dioxide, if it's made of glass, it's going to absorb almost all UV. Now, it doesn't absorb all of it. I mean, like a tanning bed, those light bulbs put out ultraviolet light, and the case of the bulb is made out of glass, so some of that UV passes through. But glass tends to absorb almost all UV. Yeah. There are some things that they say is glass. It's not really glass, like plexiglass is a plastic. It doesn't necessarily absorb UV, but glass absorbs UV.
So that could explain why, if you're ultra sensitive, you could still get a sunburn in a car.
Right, yeah. A small percentage will come through. As, to me, one of the greatest technological advances of the 20th century was sunscreen. When I was a little kid, I was one of those, I just go outside for 10 minutes and I get sunburned. And every time I go out, I get sunburned. Eventually I kind of tan, but I just get burned all the time. And so I just spent, my entire childhood, red. And it was painful, it just hurt. And then somebody came out with this stuff, here, just put this stuff on, and you don't get sunburned anymore. And so you put this liquid on, and you don't get sunburned anymore. Like, this is a miracle. How does that work? How does that sunscreen work?
It resonates at the same frequency as UV.
Yeah. I don't know what the ingredient in it is, I'm not a chemist, but I know that whatever that molecule is inside that stuff, it resonates at the frequency that matches ultraviolet light. And so the ultraviolet light comes in and hits it and gets absorbed, and those molecules shake faster and convert that energy into heat rather than into damaging energy that burns the skin rather. So if something is opaque, that means those atoms resonate at that frequency. If it's not opaque or transparent, then they don't. Yeah, what can I do for you? Caleb Bricky is here, yes. What? Why do you need to speak to him for 2 seconds?
We have microphone picture. You gotta get one picture, it'll take 2 seconds.
Okay. Caitlin, they messed up your picture and they need a new one. It takes 2 seconds. 3.
So does that mean that a material can only be opaque to one thing, or one area of light?
Well, most materials are not made of only one atom.
Okay.
Most materials are made of combinations of materials. They're mixtures and compounds. And so as a result, they typically will absorb ranges of light.
Okay. So it depends on the individual atom.
Right. And that's why in art, why different paints, different pigments have different colors. Because some pigments will absorb some wavelengths of light, other pigments will absorb other wavelengths of light, and so as a result you end up with a range of colors. To me, that's one of the things that's cool about those color-changing glasses and that kind of stuff, is something has one color, and you can do something to it and change the chemical composition of it, like add heat to it, and that will change the structure of the atoms enough that it will absorb a different color of light than it was, and therefore it changes color. Let me get this question, then I'll go here, then I'll go there. Yes?
Does that mean like tanning beds just waste a lot of energy? Or,
Yes.
So is there a material that like would be better to make them out of that exists, or do we just?
Yes.
But people are stupid.
And in fact, instead of a tanning bed, let me use incandescent lights as an example. These are fluorescent rather than but an incandescent is a regular light bulb, the old Thomas Edison type light bulb where the wire just gets so hot that it starts glowing. And in that one, it's kind of a good example because you've got all these different molecules that are vibrating. They're vibrating at different speeds in different directions, so they end up putting out all different frequencies, all different wavelengths of light, and your eye sees all of those, and we say, well, that's white light. Where in fact, you've got a mixture of infrared and ultraviolet and all the different colors of visible light. You've got all that stuff going on at the same time. So if you want a light to glow red, like a stoplight, well, you can have an incandescent bulb and you can put a red filter in it. A filter that's transparent to red wavelengths of light, but it's opaque to the other wavelengths of light. So this light bulb behind it then is putting out all these different wavelengths of light, and your filter is absorbing all of them except the red, so that the person who comes up to it sees the red light glow. Well, that means huge amounts of energy are going into producing light that you don't need at all. It just gets absorbed by the filter. That all just becomes heat. And the same thing on the green light, and the same thing on the yellow light. And again, when we get into the quantum mechanics unit, we'll talk about how an LED works. But an LED light is monochromatic. It only puts out one wavelength of light. And so when they invented red LEDs, you started seeing them around all the time, because one of the first things, I'll get your question in a second, the first thing that they did was that, well, these stoplights are incredibly inefficient because you're taking 99.9% of your energy and just turning it into heat just to get that little bit of red when the thing's on. Well, if you have a light that only produces that red light to begin with, your energy consumption goes way, way